Good afternoon, students. We'll be continuing with thread scheduling. We had completed in the last lecture, that is scheduling in real-time systems. Now we'll be starting with thread scheduling. When we talk about scheduling about the thread, there are two possibilities, that n number of processes working as one thread or one process working as one thread, as we had learnt it prior in the thread module. But now, as it is a scheduling process with thread, the criteria can be user level threads, 50 microseconds process quantum, and threads that run 5 microseconds per quantum CPU burst. So when we set two criterias, order in which threads are going to run, so here it is 1 2 3, so on and so forth, and runtime system picks a thread, one runtime will pick one thread for processing as well as process B has n number of threads, again they are waiting. Possible that A1, A2, A3, A1, A2, A3, every time you run it will go in a scheduled process, that is in the sequence. Not possibility is that every time one from A1, one from B1 is not possible, because runtime system will check the threads according to the schedule which is being given, according to the sequence which is being arranged. Now here, if kernel picks a thread and it is moved to B, then possible scheduling of kernel level threads with the same characteristics as A. There can be a possibility that same level of threads can be there in process A and process B. So that time A1, A2, A3, again possibility is scheduling in series, but also possibility is A1, B1, A2, B2, because there are same number of characteristics in A as well as in B. So kernel can pick up any thread for processing. Next is dining philosopher's problem. So you can see here there is a lunchtime in philosophy department. Now this is an example. This is just an example. You cannot say that this is actually been applied. They have given an criteria how to work on it. So we can see here that there are 5 plates and 5 spoons. So beside every plate there are 2 spoons, but they are common in sharing 2 plates, yes or no? So when I talk about a fork and a plate, how it has been done, so a problem is stated that the work of 5 philosophers is thinking and eating. Now their task is they have to use the fork for eating. Fork is that spoon. So a table is laid for them and all agreed that only food that contributed to their thinking efforts was spaghetti. So they have noodles in their plates, and what they have done is they have arranged the plates in a circular table, and what their the task is to think and put efforts for eating, nothing else. Now for eating they require fork, that is the spoon. Each philosopher requires 2 forks to eat spaghetti. Now noodles are there, so they cannot eat with one spoon. They require 2 different spoons, and for that, if each person requires 2 spoons, then somewhere at a point one person will be remaining with 1 spoon only or no spoon. So how can this problem be sorted? Like, see, the provision for eating is on a round table with a big serving pot of spaghetti. 5 plates and 5 forks are being kept there. One plate is given to one philosopher. A philosopher sits at assigned place at the table. Suppose one philosopher sits here at the assigned plate. Now he has to use 2 forks on either side of the plate. He has to use 2 forks, that is 1 and 2 on either side, that is both the sides of the plate. He takes and eats some spaghetti. Now algorithm should be designed which will allow the philosophers to eat. Now algorithm we have to design is it allows each philosopher to eat. The algorithm must satisfy mutual exclusion. Mutual exclusion here again a technical term, I'll explain it. 2 philosophers should not use the same fork at the same time. So 2 philosophers, even if they are eating, 2 philosophers, that is 1 and 2, if taken as example, they should not use the same fork or same spoon to eat the spaghetti at the same time. That is called as mutual exclusion, while avoiding deadlock and starvation. Yes, obviously, if two people share the same resource, it can be in the state of mutual exclusion, that you will learn in the next chapter, that is the next unit of deadlock. But mutual exclusion means just an reference that a common share of resource should not be handled by two different people to complete their different tasks. It can go into mutual exclusion state. Now, for this algorithm to solve, this program exemplifies basic problems in deadlock and starvation. So, either one has to be without spaghettis, or one will get food, one will not get food. So, this is the problem. The dining philosopher's problem can be seen as an example problems related to coordination of shared resources, which may occur when application includes concurrent thread of execution. Yes, exactly. Now, with you might have said ma'am is saying all these things, but yes, this is just an example, and this is a question of your university exams, that is October 2016, April 2017 and 19 also, that dining philosopher problem can be compared with your normal application, that is a computer operating system. How that can be compared? Like, if I am using same resource for my task completion, that task completion may take a lot of time, because when an application includes concurrent threads of execution at the same time, when there is concurrent thread of execution, task of execution, it will somewhere relates that some will not get resources, some will get resource and complete their task faster, some will get the resources at a late time and wait for the task completion. So, the solution here using semaphores is, following is the solution using semaphores. Now, semaphores is one technique or algorithm which is being used to solve a dining philosopher problem. Again, each philosopher picks up first the fork on the left side and then the fork on the right side. After the philosopher is finished eating, the two forks are replaced on the table. This solution unfortunately leads to deadlock. If all the philosophers are hungry simultaneously, all pick up the fork on their left side and right side fork will not be there. This is unseemly position, all philosophers starve. So, what can happen is, one solution is every philosopher picks up one spoon from the left side, eats with one spoon, then they keep down the spoon. Now they pick up, then the spoons are being changed. Again, when spoons are changed, they eat from the left side. By this, we can say that sharing of resources is possible. If not, the second problem is, simultaneously if they want to eat with both the spoons, then that time some of the person will be hungry or some philosophers will have to starve. So, this can be a problem. So, this is done according to your programming, that how they can do is, take fork I, that is first one, take fork 1 plus I plus 1, that is initialize 1, then put fork. Now, once eating is done, eat function is done, then put fork down, then 1 plus I, then the next person will eat. Likewise, we can change the dining philosopher's problem with the help of type integer semaphore algorithm, which is being used. Next is readers writers problem. When we talk about readers writers problem, yes, changes made in the problem, changes made in the conditions can give a rise to readers writers problem also. Readers means only who are accessing the data, and writers means who are changing the data. So, this can be one solution for your dining philosopher's problem. So, readers writers problem is not given in depth, but here you can say that one solution is, readers writers problem can solve a dining philosopher problem, but reader writer problem is again a different level issue which cannot be solved further with the help of semaphore or mutexes. So, this is the end of chapter 2. We will continue the next chapter we'll stop here for the day. Thank you.